Hey there. Uh, Ready to dive into something truly mind-bending?
Oh, yeah, I'm ready.
Buckle up. Because today we're exploring the world of Schubert calculus.
Schubert calculus.
Now, I know the name might sound a little intimidating, but trust me,
Right.
it's like a detective story in the world of geometry.
Yeah.
Picture this. We're trying to solve geometric mysteries,
Okay.
like figuring out how many lines
Mm-hmm.
can intersect other lines in a very specific way.
Okay.
That's what Schubert calculus is all about,
Okay.
counting these geometric possibilities.
It's like having a toolbox full of mathematical gadgets
Okay.
that can crack open
Right.
these geometric puzzles.
Yeah.
And these puzzles, believe me, can get incredibly complex.
Okay, so let's start with one of the cases that really stumped mathematicians back in the 19th century.
19th century.
Hermann Schubert, the Sherlock Holmes of geometry,
Okay.
was fascinated by this question.
Okay.
How many lines in 3D space can intersect 4 given lines?
Wow.
Sounds simple enough, right?
Yeah, it does.
But try picturing it.
Okay.
And suddenly it becomes a tangled mess of lines.
It's not just a tangled mess.
Yeah.
It's a challenge that really pushed the boundaries
Yeah,
of geometric intuition.
intuition, right?
And to make things even trickier,
Ah,
mathematicians back then
Yeah.
relied on this principle
Oh.
called the principle of conservation of number.
principle of conservation of number. It worked sometimes,
Okay.
but it wasn't exactly built on solid ground.
So it was like a rule of thumb.
Exactly.
Okay, that occasionally pointed them in the right direction,
Yeah.
but it wasn't a guaranteed solution.
It's like trying to build a skyscraper
Uh-huh.
on a foundation of sand.
Right.
Eventually, someone's going to question
Yeah.
the stability.
Yeah, I see that.
And that's where our next brilliant mind enters the picture.
Okay.
David Hilbert, in his famous list of problems that shaped 20th century mathematics,
Okay.
challenged mathematicians
Yeah.
to find a rigorous foundation.
For Schubert's work.
So to kind of solidify it.
Exactly. It was
Right.
like issuing a warrant
Okay.
for a more robust
Right.
set of mathematical tools.
Hilbert's problems are legendary.
Oh, yeah.
They're like the mathematical equivalent of unsolved mysteries.
Totally.
Yeah.
Huh.
That captivated generations of mathematicians.
Absolutely.
I can already see how this deep dive is connecting to some of the biggest moments in math history.
Absolutely.
Yeah.
And Hilbert's challenge really set off a flurry of activity.
So things started moving.
Mathematicians rolled up their sleeves
Okay.
and started developing the tools
Yeah.
needed to crack these geometric cases wide open.
I like that.
One of the first breakthroughs came in the form of Giambelli's formula.
Giambelli's formula.
Imagine trying to describe a complex geometric object
Uh-huh.
using something called a Schubert polynomial.
Schubert polynomial.
It's a mouthful, right?
Yeah, it is.
Well, Giambelli found a way
Okay.
to express this unwieldy polynomial as a determinant,
As a determinant.
a mathematical tool that's much easier to work with.
Hold on. So before Giambelli came along,
Right.
mathematicians were essentially wrestling with these complicated polynomials.
Yeah.
What kind of computational nightmares did this formula help them avoid?
It was a bit like trying to solve a giant Sudoku puzzle
Okay.
without any strategies.
I see.
Giambelli gave mathematicians a set of elegant techniques
Okay.
to simplify these calculations.
Right.
Suddenly, what seemed impossible
Yeah.
became manageable.
Well, so Giambelli provided a crucial tool in our detective kit.
Exactly.
That's the next piece of the puzzle.
Well, another breakthrough came in the 1920s
Okay.
with the Peary rule.
Peer rule.
Now, this one might sound a bit abstract,
Aye.
but it's all about understanding intersections.
Intersections.
Imagine you have two Schubert varieties.
Okay.
These are the geometric objects we're investigating,
Right.
and they intersect in
Yeah.
a specific way.
Okay.
The Peary rule helps us understand how that intersection relates to the intersection of one of those varieties with something simpler,
Okay.
a linear subspace.
You know, I'm usually all for analogies,
Right.
but that one kind of went over my head.
Sure.
Can we make this a bit more concrete?
Okay.
What does the Peary rule actually allow us to do?
Okay, let's think about a real-world scenario.
Okay.
Imagine you're an architect
Okay.
designing a building
Uh-huh.
with a complex curved roof.
I see.
The Peary rule would be like having a set of guidelines
Yeah.
that tell you how different sections of that roof
Right.
can intersect and connect with each other,
Yeah.
ensuring that the structure is stable
Okay.
and aesthetically pleasing.
Ah, okay. Now I see the practical implication.
Yeah.
So it's like a blueprint for how these geometric objects can interact
Precisely.
without creating chaos.
And then in the 1930s, things took an even more interesting turn.
Oh, really?
Mathematicians uncovered a hidden passage between Schubert calculus and a seemingly unrelated area of math.
Wow.
Symmetric functions.
Symmetric function.
Specifically, they found a connection to something called Schur functions.
Okay, I have to admit, I'm intrigued.
Yeah.
Why is this connection to Schur functions so important?
It's like discovering a hidden tunnel that connects two seemingly separate mansions. Suddenly you realize there's a whole new wing to explore.
Nice.
Full of hidden treasures and connections you never imagined.
Okay.
This connection revealed that concepts from symmetric functions could be used to shed new light on problems in Schubert calculus.
Wow.
Leading to new ways of thinking about geometric intersections.
Now that's what I call an aha moment.
Exactly.
It's amazing how math reveals these unexpected connections between seemingly different fields.
It's one of the things that makes math so endlessly fascinating.
It is.
Yeah.
And believe it or not, the story doesn't stop there.
Oh, really?
In fact, in the 21st century, mathematicians decided to shake things up even further.
Oh, wow.
By introducing a dash of randomness into the equation. Randomness in Schubert calculus.
Yeah.
That sounds almost counterintuitive.
Right.
We've been talking about precise counting, exact intersections. How does randomness fit into this world of geometric certainty?
It's a fascinating twist that really pushes the boundaries of what Schubert calculus can do.
Yeah.
Think of it this way. Up until now, we've been focused on finding the precise number of lines that satisfy certain conditions.
Okay.
But what if instead of asking how many times you hit the bullseye, we ask about your average score in a game of darts? That's the essence of probabilistic Schubert calculus.
Probabilistic Schubert calculus.
It's about looking at the average number of intersections.
Average.
As if our geometric objects were randomly scattered in space.
I see. So instead of being laser focused on exact solutions, we're taking a step back and asking about the statistical likelihood of certain intersections occurring. I have to say I'm a bit skeptical.
Okay.
Why is this probabilistic approach so valuable?
Well, for one thing, it opens up a whole new set of problems that were previously intractable.
Okay.
Imagine trying to count intersections in a space with thousands of dimensions.
Okay.
The calculations would be astronomically complex.
Right.
But by introducing probability, we can start to make sense of these high-dimensional spaces in a way that was never possible before.
So it's like trading in our magnifying glass for a wide-angle lens.
Exactly.
We're sacrificing some precision, but gaining a much broader perspective.
Exactly.
Are there any practical applications of this probabilistic approach?
Absolutely.
Does it connect to any real-world problems?
One of the exciting areas where probabilistic Schubert calculus is making waves is in the field of data science.
Data science.
Think about trying to analyze massive data sets with millions of data points using traditional methods. It would be nearly impossible to find meaningful patterns or connections.
I can see that.
But by applying the tools of probabilistic Schubert calculus, we can start to uncover hidden relationships and make predictions about future trends.
So we can use it to, like, predict things.
Exactly. It's like having a mathematical compass to navigate the vast and complex world of big data.
Okay, now that's what I'm talking about.
Yeah.
This probabilistic approach seems like it has the potential to revolutionize how we analyze and interpret data.
It really does.
It's amazing how an abstract mathematical idea can have such real-world impact.
It is pretty amazing.
But I do have to ask, who's the mastermind behind this probabilistic revolution?
One of the key figures in this field is Peter Bergeser.
Peter Bergeser.
His work has been instrumental in developing the theoretical foundations of probabilistic Schubert calculus and exploring its connections to other areas of mathematics.
I love how this deep dive has taken us from 19th century geometric puzzles to cutting-edge applications in data science. It really highlights the dynamic and ever-evolving nature of mathematics.
Absolutely.
But before we get too carried away with these modern developments, I want to loop back to something you mentioned earlier.
Sure.
Generalized Schubert calculus.
Generalized Schubert calculus.
Sounds like mathematicians are taking the core ideas of Schubert calculus and stretching them even further.
That's exactly right. Generalized Schubert calculus is all about taking those tools and techniques we've been discussing and applying them to even more abstract mathematical objects and theories.
So we're not just solving geometric mysteries anymore.
Right.
We're entering a whole new dimension of abstract mathematical puzzles.
Exactly.
I have to admit, I'm struggling to grasp the implications of this generalization. Can you give us a specific example?
Well, one exciting area is in the study of representation theory.
Representation theory.
This branch of mathematics deals with understanding symmetries and how they can be represented using linear algebra. It turns out that some of the core concepts from Schubert calculus, like Schubert varieties and classes, have natural counterparts in representation theory. By applying these ideas, mathematicians are uncovering deep connections between geometry algebra and the study of symmetry.
Now, that's what I call a mind-blowing connection.
It is.
It seems like the deeper we dive into Schubert calculus, the more interconnected the world of mathematics becomes.
Absolutely.
But, you know, I'm eager to see these abstract ideas in action. We've been talking about counting lines and intersections, but I'm craving a concrete example. Can we bring this back down to earth and see how Schubert calculus actually works in practice?
Absolutely. And luckily, the Wikipedia entry on Schubert calculus provides a perfect example. That demonstrates the power of these techniques, calculating the number of lines that can lie on a cubic surface.
Okay, now we're talking a cubic surface. I can visualize that.
Right.
But how on earth do we go from this three-dimensional object to the abstract world of Schubert calculus? Walk me through this. I'm ready to see the magic unfold.
Let's break it down first. We need to understand how lines in 3D space can be represented within the framework of Schubert calculus. Remember, each line can be thought of as a two-dimensional subspace in a four-dimensional space. This allows us to represent lines using something called Schubert varieties.
Schubert varieties.
Which are specific geometric objects within a larger space called a Grassmannian.
So we're essentially translating the problem of lines on a surface into the language of Schubert calculus.
Yes.
It's like creating a mathematical dictionary.
Precisely.
To bridge these two worlds.
And each Schubert variety has an associated Schubert class.
Which acts as a sort of mathematical fingerprint.
A fingerprint.
Capturing information about that variety.
I'm following so far. We've got our lines translated into Schubert varieties. Each with its unique fingerprint. But how do we actually count the lines on that cubic surface? What's the next step in our investigation?
Here's where we bring in our heavy artillery Churn classes.
Churn classes.
Think of them as powerful tools that allow us to extract even more information about those Schubert varieties. It's like having a set of high-powered lenses that reveal the intricate details of these geometric objects.
So churn classes help us zoom in and analyze those Schubert varieties with even greater precision.
And there's a specific formula called the splitting formula. That comes into play. It helps us break down complex mathematical expressions into simpler, more manageable pieces. Imagine trying to solve a giant jigsaw puzzle.
The splitting formula is like having a guide that shows you how the pieces fit together.
So we're strategically breaking down the problem. Into smaller chunks. We've got our Schubert varieties, our churn classes. And this splitting formula to guide us. I'm on the edge of my seat. How does all of this lead us to the number of lines on a cubic surface?
Well, by carefully applying these tools and following the steps laid out by Schubert calculus, we arrive at a truly remarkable result. There are exactly 27 lines on a cubic surface.
Wow, 27.
27.
That's such a specific and unexpected number. It's incredible how this seemingly abstract mathematical machinery can produce such a concrete and elegant result. You know, at the beginning of this deep dive, I was a bit intimidated by the name Schubert calculus, but honestly, it's been like going on a thrilling detective adventure.
I'm glad to hear that. And you're right. It's a testament to the power of Schubert calculus that it can take us from a seemingly simple question. How many lines on a surface to a journey through abstract spaces, powerful formulas, and ultimately a precise and beautiful answer?
This deep dive has definitely broadened my perspective on what math can do. We've explored everything from 19th century geometric puzzles to modern applications in data science, and even connections to other fields like representation theory.
It's amazing.
It's truly mind-boggling.
It really highlights how interconnected and dynamic the world of mathematics is. And who knows what other mysteries and applications Schubert calculus might help us unlock in the future.
Well said, and for our listeners who are eager to explore further,
yes,
we'll be sure to include some resources in the show notes. But before we wrap up, I want to leave you with a little challenge.
Okay.
Can you visualize a cubic surface with its 27 lines? It's a tough one, but I think it captures the essence of what Schubert calculus is all about, unveiling the hidden structures and patterns that shape our world.
It's a challenge that invites us to bridge the gap between the abstract and the concrete, to see the beauty and complexity of mathematics in a whole new light.
And on that note, we'll bring this deep dive to a close until next time. Keep exploring, keep questioning, and keep diving deep into the fascinating world of knowledge.